Assalamualaikum warahmatullahi ta'ala wabarakatuh. Today I'll be presenting my research titled Development of an Intelligent Smart Classroom Energy Saver System Using Machine Learning for Adaptive Energy Control. So educational institutions consume a large amount of electricity every day because classroom appliances such as lights, electric fans, and air conditioning units are continuously being used. So the problem is that these devices are often left on even when classrooms are vacant or only partially occupied. So because of this, it leads to three major problems. First is unnecessary energy consumptions because electricity is being wasted. Second is increased operational expenses since schools pay higher electricity bills. And third is higher carbon emissions, which negatively affects the environment. So according to related studies, buildings consume around 40% of global energy usage, which shows how important energy management is. Another study found that classroom lighting systems stay on for an average of 10.7 hours daily even without occupants. So the good news is that studies also show that control system can reduce energy consumption by more than 60%. So here in the Philippines, rising electricity costs have made classroom energy management is a serious issue for educational institutions. So because of these problems, my study aims to provide an automated and adaptive solution that can reduce unnecessary electricity consumption inside the classrooms. So objectives. So the main objective of my study is to develop an intelligent smart classroom energy saver system using machine learning for adaptive energy control. So specifically, the system aims to monitor classroom conditions in real time, detect occupancy, analyze environmental data using machine learning, and automatically control appliances and reduce unnecessary electricity usage. The system design, input process output, IPO model. So input includes occupancy data, temperature data, light intensity data, sensor readings, and machine learning datasets. Purposes includes data collections via sensors, environmental monitoring, machine learning analysis, adaptive decision making, automated appliance control. And output is reduce energy consumptions, automated energy management, improve efficiency, and adaptive energy saving. So this is the flow chart of my system. So methodology and components. So my research uses a mixed method experimental design with an agile iterative development approach. So the hardware components include ESP32 for microcontroller, PIR sensor for occupancy detections, DHT22 for temperature and humidity, LDR sensors for light intensity, relay modules for switching appliances, and PZEN0040 for energy monitoring. So for machine learning algorithms, we consider decision tree, random forest, and support vector machines. So these algorithms help classify occupancy and predict energy consumption patterns. So this slide presents the data treatment and statistical analysis used in the study. These statistical tools help the researchers analyze energy consumptions, evaluate machine learning performance, measure system effectiveness, and determine whether the proposed system significantly reduces energy usage. So for the first sub-problem, the researchers use descriptive statistics such as mean, standard deviation, minimum, and maximum values to analyze classroom energy consumption patterns. So the mean was used to get the average energy usage, while standard deviation measured how consistent or valuable the energy consumption was. So for machine learning model optimization, the researchers evaluate the performance of the algorithm using accuracy, precision, recall, F1 score, and EUC, ROC. These metrics help determine which algorithm perform best in predicting occupancy and controlling classroom appliances. So for the third sub-problem, the researchers evaluate the effectiveness of the system architecture using mean absolute error, inference latency, reliability percentage, and system uptime percentage. This metrics measures the prediction accuracy, response speed, reliability of the relay module, and overall stability of the system. So the research will also evaluate the overall accuracy and reliability of the system using classification metrics compared against a 90% benchmark. So the system performance was further analyzed based on classroom conditions and time of day to ensure consistency. So for the final sub-problems, percentage reduction analysis was used to measure energy savings before and after system implementations. So a paired sample t-test with a significance level of 0.05 was conducted to determine whether the reduction in energy consumption was statistically significant. So lastly, payback period analysis was used to estimate how long it will take for the system cost to be recovered through energy savings. So the limitations and assumptions. So the limitation conducted with a selected Sulay State University in classroom only, focus on lighting, electric fans, and air conditioning units only. Machine learning model trained on locally collected classroom data, limited to design, development, and testing phases. So assume stable power supplies, exclude power outage. So key assumptions, sensor data accurately reflects actual classroom conditions, and appliances can be integrated with relay modules without wiring chains. Classroom schedules are consistent across semesters, and stakeholders will cooperate during the data collections. Hardware will operate reliably under normal classroom conditions. So, expected outcomes and significance. We expect the system to reduce unnecessary electricity consumptions, achieve at least 90% accuracy, create smarter and more energy efficient classrooms, and contribute to environment sustainability. So the beneficiaries of this study includes students, faculty, administrators, future researchers, and educational institutions. So that's all. Thank you.